All right, so I think we should start. And today is the third to the last colloquium of the season. Temperatures are rising a little bit finally. And it's a pleasure to have Jordan Cotler with us today. Jordan obtained a bachelor in physics and mathematics from the MIT, PhD from Stanford University, and he's particularly interested in non-perturbative aspects of gauge theory and gravity, in particular pertaining to the early universe cosmology and black holes. Other interests are quantum information theory, computational complexity theory, especially to develop algorithms for quantum computing. And today he's going to talk about the black hole microstate statistics and mesoscopic quantum gravity.
Great, thank you so much for the nice introduction. It's nice to be here and give a talk for all of you and to be on the other side of the audience. So I'm going to tell you about some work in progress, hopefully to appear soon in collaboration with Christian Jensen, hopefully a paper to appear in the next few weeks. And the subject of the talk is black hole microstate statistics and mesoscopic quantum gravity, which is quite a mouthful. And I'll tell you in turn what each of these different things means as we go along. And of course, feel free to ask questions throughout. So let's begin with some of the big questions, the kinds of questions that we would like to try to chip away at a bit in this talk. So a fundamental question that we'd like to ask in quantum gravity is, what is the fundamental substructure of space-time? Is there a more fundamental structure to space-time than that which we experience or observe as we go about our day in the world? And moreover, if there is a more quantum substructure of space and time, how does this microstructure then give rise to a classical description, the smooth space-times that we think about in the context of general relativity or otherwise? Another question is, how do we describe the interior of a black hole? This is a mysterious question for even realistic black holes, even at the classical level. What we're going to do is we're going to bring to bear contemporary tools of quantum gravity, in particular string theory, to try to chip away a bit at this question. In particular, the question is, to what degree is this question accessible? Namely, the question of what is the interior of a black hole? To what degree is it accessible in non-perturbative models of quantum gravity, for instance, string theory?
Of course. The framing question. Why are those two things linked, like in your mind, like the substructure of space-time and what's inside of the black hole?
Well, there's a few different reasons. So one of the reasons would be understanding the black hole singularity. For example, this is a particular instance in which the microstructure of space and time, that I think would be the ultimate goal to understand. And also in recent developments, and even maybe not so recent developments, about understanding how it is that black holes scramble up information, how it is that when you throw things into a black hole, whether information escapes from it. To understand that the resolution to the way in which black holes rearrange or reorganize information, we need to have some control over potentially the microstructure of space and time to understand how the degrees of freedom get reorganized by a black hole. So I would say those are the kind of two main reasons why I would pair these questions together.
Yeah, thanks.
Sure. So the talk's going to be divided into 4 parts. In the first part, I'm going to talk about black hole microstate statistics. So I'll tell you what that means, but it's going to be, roughly speaking, allowing access, building some quantum description of black holes and being able to use techniques, the gravitational path integral, some techniques kind of coming from string theory in order to understand aspects of black holes conceived of as a quantum object. And then what we're going to do is we're going to take these considerations, we're going to embed them into the paradigm of ADS-CFT, which I will briefly review. That's what we'll do in the second part of the talk. In the third part of the talk, we'll see how, in trying to better understand black hole microstate statistics in the context of ADS-CFT, this will necessitate an expansion of our understanding of the ADS-CFT correspondence, the inclusion of new entries in the so-called holographic dictionary, which I'll explain what that means. But the ways in which these new insights about black holes are going to augment our understanding of ADS-CFT are going to lead to what I believe is a new and emerging picture of a way to think about quantum gravity, which I'll call mesoscopic quantum gravity. So that's the arc of the talk. We'll build up to the later elements, and hopefully they'll be more understandable as we come to them in turn. So in the first part, as promised, I'll talk about black hole microstate statistics. So here's a picture of a black hole. It's not as nice as the one, there's a real picture of a black hole. But famously, a black hole radiates approximately thermally with a temperature which is inverse in its mass due to quantum effects. And it has a finite entropy, which is proportional to the horizon area divided by 4G Newton. These are the famous kind of facts about black holes that you would want to tell your friends about. Now, if we look at the reduced density matrix of a black hole, it should look approximately like a thermal state. So this is just a Gibbs state here. We have energies and we have energy eigenstates. And we call these states, which have a fixed energy, the black hole microstates. They are the microstates in the sense that you would talk about microstates in the context of quantum statistical mechanics. And because a black hole is an approximately thermal object, we also anticipate that it should also bear a description in terms of these states E sub I, which are states of roughly fixed energy. Now, a difficult non-perturbative question in quantum gravity is, what are the black hole microstates and what are their energies? If I give you a quantum system, one of the first things that you might want to know about it, if I give you, say, the Schrodinger equation, is what are the energy levels? What are the energy eigenstates? Because a black hole is a quantum object, which is approximately thermal, there are energy states and there are energies in the game, and it would be nice to be able to have some precision understanding of what they are, to have some understanding of what geometry they correspond to and what properties they have. As I'll explain, this is a very difficult question to compute. But nonetheless, we're going to focus in particular on the question of not the energy eigenstates for the moment, but the question of what are the energies that I should associate with this system, and what are the properties of those energies. So here is an example of a cartoon of what you might expect the energy spectrum to look like that would correspond to microstates that correspond to a black hole. So here there are several features of just this energy spectrum, as are true of all energy spectrums. One is that the density of the energy spectrum is changing at higher and higher energies. It starts off with large separations, and the separations become more and more tightly knit as we go to higher energies. There's another feature, which is the mutual relationship between between nearest neighbor energies and the way that the energies correlate with one another. So it's not just that they're becoming tighter and tighter and tighter as we go to high energies. It's the fact that the energies have a proclivity not to want to be near one another. They're not piled up in particular locations. They have some notion of level repulsion, which is a phenomenon that you often have in chaotic quantum systems. So there was a very famous computation that was done in the work of Hawking, Gibbons, and Perry in the mid-70s, in which they were able to compute the coarse-grained density of states by a path integral computation. So if we take these energy levels and we smear them out, if we take these energy levels and we smear them out so that we just look at the density of the states, how tightly knit the energy levels are getting, then we get a smooth profile that I'll call the coarse-grained density of states. And what's remarkable is that this computation that was done in the mid-70s show that there is a computation that can be done using the gravitational path integral. When you take Einstein gravity, you stick it into the Feynman path integral, and you try to find a saddle point approximation, as we often do, that actually gives you access to this coarse-grained density of states. So there's a semi-classical computation which gives rise to this. So even though we can't access the actual individual energy levels, we can access statistical properties. We can access the coarse-grained density of states as opposed to the individual levels or individual eigenstates.
So this only assumes the usual mechanics of the path integral formulation and Hawking's results about the entropy. And
precisely, and it's valid in effective field theory. So it's something that is a true statement about astrophysical black holes. It's very robust and works in many different contexts. However, this gives us only limited information. This is just the coarse-grained density of states, and there's more to life than just the coarse-grained density of states. So one thing that we can do, so let's zoom in on a part of the spectrum. So let's zoom in on a part of the spectrum in which the density of states is like locally constant, so that within this little window that the average level spacing is roughly fixed. Now we can look at it as the mutual interrelationships between the energy eigenvalues themselves. And the energy eigenvalues, these different energies, their average level spacing, the delta between them, is non-perturbative. It goes like e to the minus 1 over g newton. So this is something which you can't access in perturbation theory in small g newton. So, however, what we might be interested in is understanding the level statistics. Again, like for example, how close do individual levels get near each other on average? This is the next most refined quantity that you can understand after the density of states. Yes.
So I would imagine that there will be degeneracies, right? For instance, azimuthal quantum number m, changes may not have any effect on the energy. So how are you treating those? Do you consider them, because they are right on top of each other, there's no repulsion there.
Yeah, so let me make a quick comment that I think will lead into an answer to your question. So something that you would expect, I'll talk about the issue of degeneracy in a moment, it's a good question. Something that you would expect in the context of, if I gave you just a spectrum of some system like a black hole, you can say, well, what would you expect it to look like? So there's an old subject that goes back to the 1950s and 60s in nuclear theory, which was developed by Wigner and Dyson and others, the subject of random matrix theory, in which they wanted to understand, given a strongly interacting nucleus, what do the energy levels look like? But this question is a strongly coupled question. It's an almost impossible question unless you can answer it using, sophisticated numerical simulations, which were not available at the time and which are still essentially barely available for this particular question. So what they did is they said, well, suppose that the Hamiltonian of the system is a random matrix in a particular sense. Are there features of the energy levels that you would anticipate as arising from a random matrix, which have universal properties that you would expect to find empirically in the actual level spacings of heavy nuclei? So they developed a theory of random quantum systems and showed that there were certain features which would map onto the particular quantum systems of the heavy nuclei. And what was later understood is that these matchings should be robust, that there should be a correspondence between these random systems and these particular strongly interacting systems. In the case of the strongly interacting system in question is chaotic, that the subject of quantum chaos is in a certain sense predicated on these kinds of connections between strongly interacting chaotic systems and random counterparts, such as random matrix theory. Now, to answer your question, the caveat is that when the cases in which you can make this matching is you have to be careful about symmetries. The reason that we often have degeneracies is due to the presence of symmetries. So what you do is that you take your Hamiltonian and you block diagonalize it according to symmetry charges. And when you look at a block which has fixed charge, that it is only within blocks where you have diagonalized out all of the symmetry charges, that there you do not expect there to be degeneracy, and that's where the random matrix theory will hold. So that's the answer. So whenever we have black holes, for example, with angular momentum with charge, we're going to work in sectors of fixed angular momentum and fixed charge. Thank you. So something that you expect from this random matrix theory analysis is a certain kind of level repulsion that I alluded to before, that the energy levels do not get that close to one another. They have a proclivity to seemingly repel. Now, what we've been able to establish, building off of earlier work of Saad-Chamber at Stanford, I can explain some of the technical differences, is that in this computation, oh, sorry, I shouldn't want that one, which is in this computation that was done in the 70s, essentially there is a configuration that has one asymptotic, it's like a space-time that it's Euclidean, so it's a Euclidean signature, that gives you the density of states that has one asymptotic boundary. It turns out that if you want to understand energy statistics, if there's two energies that you would like to compare, it turns out that the kind of quantity that you should compute in the gravitational path integral is a quantity with two boundaries. It turns out that the intuition is that the number of energies which you would like to compare with one another, if you want to look at energy statistics, then you need to look at something with two boundaries. If you want to look at energy, if you want to compare three different energy scales, then you need to look at something with three boundaries. But the point is that by doing computations which are valid and effective field theory using the Feynman path integral, we can access information about the level repulsion of the black hole microstates and more refined information about the spectrum. Still coarse-grained, but nonetheless, it's more refined information than what we could previously access. So let me give you an example, and then I'll talk about it a bit more of a high level, just to show you some of the machinery that was developed to do this. Some people in the audience have heard earlier versions of this. Let's talk about the example of ADS3 quantum graph. For technical reasons that I can explain later, we're going to consider spacetimes with a negative cosmological constant. Later, we can talk about flat space and de Sitter space. This is just the technically easiest case. And we'll think about, for the moment, three space-time dimensions. We live in four, but let this again will simplify the calculations for the moment. Somewhat this. So a computation that was done by Maloney and Witten in 2010, building off of the work of others, did the version of this Hawking-Gibbons barrier calculation where for 3D black holes, they were able to access the coarse-grained density of states via a computation of the path integral. Turns out there's a slightly different way of rephrasing the result that is more amenable to generalizations. So as we were discussing before, here for these kinds of black holes that we're going to be interested in 3D, there's two quantum numbers. There's not just the energy, but there's also the angular momentum, which I'm going to call J. So we're going to consider the density of states as a function of energy as well as of being in a limit. So now another computation is that we would like to be able to understand the level repulsion of the black hole microstates in 3 dimensions. And we can do this by looking at a two-sided wormhole. Now, a difficulty is that there are no smooth saddles of the Einstein-Hilbert action that correspond to a wormhole like this, that have boundaries which have flat or positive curvature. Now, the way that this computation works is essentially by a saddle point computation. The way that we usually do the path integral is we try to find saddles. We do a saddle point or stationary phase approximation. Unfortunately, in the context of trying to find these wormhole solutions, no such saddles are available. In fact, you can prove that they don't exist. However, there is the next best thing to saddle points, which are called constraint samples. And let me briefly tell you what a constraint saddle is before we come back to the computation. So we can think about a saddle. When we have an integral, we perform a saddle point approximation. It's like a point at the bottom of a ball. A point at the bottom of a ball is a point which, if you put a ball down there and you give it a little kick, it's stationary and in fact stable in all directions that you can fluctuate. Now, what a constraint saddle is not like the point at the bottom of the ball, but like an alpine slide. So we have a person in the slide, and in the slide, if you fluctuate to the left and to the right, you're stationary. In fact, you're stable. That you'll just dip back down to the middle of the slide. But there's also an up-down direction to the slide in which you're not stationary. So a constrained saddle in the path integral is like a saddle point where you are stationary in infinitely many directions in field space except for one. There's one direction in which if you look at fluctuations, you can go up, you can change the action by going uphill or downhill. So in other words, the logic of these constraint saddles, which have been used a lot in the context of gauge theory, is that what you do is you perform a saddle point approximation in all of the directions in field space in which you're stationary, except for the one in which you're not stationary. And in that direction, you explicitly perform the path integral. So in any case, we can leverage the technology of constrained saddles to be able to compute the level statistics. Yes, question.
In the diagram, so the thing on the end, sorry, not that this one, the other side. Yes, so that's a torus, and that ring is supposed to represent the torus.
Yeah, so it turns out that in EDS3, the topology of the boundary of the space-time is that of a torus. And a torus can be parameterized by a complex structure, which is tau. It can be a complex number, which specifies the way in which the two cycles of the torus interface with one another.
Is that like a compactification Euclidean signature? Is that what it is?
That's exactly right. The reason why you have a torus is essentially because the time direction is compactified to Euclidean circle. That's right. So let me maybe jump ahead and explain some features of the answer. So what we do in this computation is we look at the gravitational path integral. This is just the gravitational path integral where we've done some gauge fixing for diffeomorphisms. And we perform this constrained saddle computation with these two asymptotic boundaries. And let me distill part of the answer for you. Let me make a technical comment. It's not so conceptually important. We're going to restrict to states that have fixed energy, which correspond to primary states in the context of the Virasoro group. So we have to diagonalize the symmetries of this system, and we're going to look at a particular set of states which have fixed angular momentum, which correspond to Virasoro primaries. That's not familiar, don't worry so much about it. But here's the answer that we get right here. This is the answer that we get for the level statistics. So now let me show you something that I find quite remarkable. So this is a computation which is done in the context of quantum gravity in the path level. So it turns out that there is a different computation in random matrix theory, the theory of random systems, which was really kind of made robust by Eynard and Ronton, maybe about 15 years ago, in which they showed that the answer that we would expect to find from random matrix theory would be this answer. I'd like to draw your attention to the similarities between these two answers, that in fact, that they precisely match with one another, down to the factors of 2i. But the answer that you would expect for the statistics of the energies that comes from random matrix theory is precisely the answer that you get from the gravity computation. Yes,
So the delta on that J is because the charge is predicted by symmetry. Is that what it is?
exactly. So I was about to, so let me point out some features of this. So one of the features, as you were saying, is this Kronecker delta. The Kronecker delta says that we expect that sectors with different angular momentum will be decorrelated. In other words, that we only expect non-trivial correlations between sectors and between a sector and itself with the same fixed angular momentum J. Okay, so that's there. We also have this prefactor, which we can talk about shortly, which it turns out encodes long-range level repulsion in the spectrum of black hole microstates. Then we also have these exponential factors. It turns out that what the exponential factor is supposed to be in random matrix theories, it tells you the threshold energy where the density of states begins. Now, what this should correspond to in the black hole setting is the energy of the lightest black hole, in this case, BTZ black hole, since we're ADS3, of spin J, of angular momentum J. And in fact, that's exactly what this is. This number here is precisely the energy of the lightest black hole of spin J, or of angular momentum J. So this is a remarkable match. This is a quantitative match, again, between a random matrix theory formula about what you would expect the level systems to be, and a computation solely done in gravity. So, this answer did not assume that answer and vice versa. Yes?
Just a notational thing. I thought the betas were temperatures. What is beta 1, beta 2 here?
Right. So the way to think about this is that you're essentially comparing, so the answer the thing that we're really interested in is the correlations between an energy E and an energy E prime and J prime.
Yeah.
We're going to essentially take the double Laplace transform with respect to beta 1 and beta 2. So the way you can think about this is it's looking, roughly speaking, at the correlations between the energies of a black hole at inverse temperature beta 1 and another black hole at inverse temperature beta 2. That's what's being compared. Wow. So what we see, in fact, is a pattern of universal energy level repulsion. That's what this answer encodes. So let me make a few, just a kind of a technical aside. So let's examine the form of the answer. So here's schematically what the answer looks like. Let's not worry for the moment about the issue of fixing the angular momentum. So we're going to do something which seems like a peculiar mathematical move. We're going to take the beta 1, beta 2, which we usually associate with inverse temperatures, real numbers. We're going to take them to be beta plus IT and beta minus IT, where we associate the T with a kind of time. If you will, this is like kind of mixing between real time and imaginary time. Let's not worry so much about the interpretation of this. But if we just plug that into here, then this is the answer that we find, which for large capital T goes like e to the minus 2 beta E naught times T. It looks linear for large T. So we see that in this answer that we have a threshold energy. This is the energy in our case of the lightest black hole in the spectrum. And then this is a linear ramp. So the threshold energy, as I said, is the minimum energy in the spectrum, the energy of the lightest black hole and the classic black holes under consideration. And the linear ramp, it turns out, implies the long-range level repulsion of energy levels. When you see this linear ramp, that tells you that the energy levels have a proclivity to repel in precisely the way that random matrix theory prescribes. So now what about higher dimensions? So it turns out that, at least in the context of anti-de Sitter, we can also do this in flat space, it's a more recent development, we can consider all higher dimensions. So we did 3 dimensions, we can do 4, 5, 6, and so on.
Sorry, on the repulsion,
Yeah.
is it just a nearest neighbor repulsion, or are there higher order correlative repulsions?
So what this is capturing is the repulsion between, so how do I say? Because there is nearest neighbor repulsion, this imprints itself also onto the repulsion of eigenvalues, which are order 1 number of level spacings apart. You can think about it kind of like a crystal. In a one-dimensional crystal, if you arrange the eigenvalues, in which, because of the fact that the nearest neighbor eigenvalues repel, this will induce certain long-range correlations between eigenvalues which are a bit further apart. So in other words, you expect, for example, that one eigenvalue here and another eigenvalue here, that if there are k eigenvalues apart, then you would expect roughly on average there not to be an eigenvalue so much. It's kind of k times the level spacing away, roughly speaking. I mean, you can examine sort of how well it's a perfect crystal, given the fact that, asking how much, maybe I'm just sort of foaming around my words, but yes, the answer is the short range level repulsion reduces long range level repulsion. The thing which is most directly measured by this is the long range level repulsion at order 1 number of level spacings. To see the actual nearest neighbor repulsions directly requires a much more difficult computation. computation, which we don't know how to do. So in higher dimensions, though, we find that there are also these kinds of constraint saddles, which are perturbatively stable. They encode the threshold energy and the long-range level repulsion of energy levels. So this doesn't just work in 3D, but it works in all higher dimensions. And the simplest form of the answer that you get, at least by the simplest computation, is indeed you find the energy of the lightest black hole, and you find a linear ramp. So this also works in general for charged black holes. We're also trying to understand how to do spinning black holes. It works in various ways in the context of asymptotically flat space, maybe more relevant for astrophysical black holes. So we can see that in these different examples, even in more realistic models in higher dimensions, we still see that a computation in the path integral tells us information about the level repulsion of the black hole microstates.
Do you get a phase transition at the page temperature? Higher-dimensional calculations?
Yeah, let's discuss that. That's an interesting story. Let's talk about that maybe a little later. But yes, you can see different effects related to that. Okay, so now the computations that I told you about are in the context of just effective field theory, in the context of semi-classical quantum gravity. They have nothing to do a priori with string theory or UV completions. They're all computations which look at quantum gravity from long distances. Okay. So it makes no assumption about what is going on at microscopic scales, which is actually a little conceptually surprising. One of the weird features of these computations, I would say, is that by doing computations which are valid in effective field theory, namely at long distances, we can't infer precisely microscopic properties of black holes, but we can infer statistical properties of the microscopic properties of black holes. So that's an interesting conceptual point that we'll return to. And now let's talk about ADS-CFT, which is a setting in which we can understand potentially non-perturbative physics, or we can understand more details about the microstructure of space and time, because ADS-CFT, as I'll explain in a moment, in principle provides a manner in which we can fill out all of the details of quantum gravity all the way down to the Planck scale, in principle, even if we don't know how to do it. So there are two, I would say, main paradigms for quantum gravity, or at least two that I would like to discuss. One is the context of perturbative quantum gravity as an effective field theory. This is the paradigm in which we've been working so far. Namely, what you do is that you look at a space-time that you're interested in, maybe a black hole, maybe a flat space, and you look at tiny little fluctuations around it, and then you define the Eigenvalues. Now, the problem, of course, is that Einstein gravity is not a renormalizable theory, but nonetheless, we can still do computations in perturbation theory. Of course, we have to add in more renormalization constants as we go to higher loops, but nonetheless, we can still proceed in the program of understanding quantum gravity as an effective field theory. Now, a different way of conceiving of quantum gravity is in a non-perturbative fashion, namely quantum gravity in the context of ADS and string theory. So, as is well known, there is this very famous and celebrated duality between string theory and anti-de Sitter space. Namely, if you take anti-de Sitter space in d+1 dimensions, that is d dimensions of space, 1 dimension of time, then there's a duality between that and a conformal field theory, which is in 1 spatial dimension less. Here's what's weird about this. This is a theory which has strengths and gravity and space-time and in a certain sense looks like our universe, except it has a lot of additional symmetries and a negative cosmological constant, but this is a good model, a sophisticated model of quantum gravity. What's interesting about what it is dual to, this conformal field theory, is that it has 1 less spatial dimension and it has no gravity. It's just a field theory without Einstein gravity touching it at all. So what's interesting is that across this duality, you not only grow an additional dimension of space, but the gravity itself and gravitational dynamics are emergent somehow from the description of the conformal field theory. That's what's surprising about the ADS-CFT duality. So what's nice, though, is that this offers us an opportunity, since this is in principle a non-perturbative duality. If we understand the conformal field theory side very, very well, we can then in turn gain insights into what's going on the gravity side. And since we often have a lot of control over conformal field theory, this has been a fruitful kind of duality to be able to infer properties of the anti-de Sitter space of quantum gravity by learning properties of CFT. However, I should mention, if you also love CFTs, and that's your goal to understand CFTs, you can also take insights on the gravity side and have that teach you things about CFTs, which has also been a fruitful enterprise. We're going to be interested in really understanding gravity science. So yeah. So okay, so this is a little bit technical, but this is just to sort of prove a point. I've given you these wormholes that are in Einstein gravity and anti-de Sitter space. Can we actually embed these in a full-fledged way into the context of ADS-CFT, the original example of Maldacena, which is called just type 2B string theory on ADS5 cross S5. This is the original example of ADS-CFT due to Maldacena in '97. And okay, so now that we're in full-fledged string theory, well, the low energy limit of the theory is type 2B supergravity, which has a lot of it, which doesn't just have the graviton and the gravitino, but has additional matter fields. It has fermions, including the gravitino, and also interesting gauge degrees of freedom. So we would like to see if we can find wormholes in this context, which are also stable, so that we can have a robust computation using the gravitational path integral. So in fact, these kinds of configurations in type 2B supergravity do exist. Here's what they look like. It's not worth dwelling on this so much. This is the metric degrees of freedom. This is the dilaton is constant. This is the phi form flux. All the other fields have a trivial profile. Fermions don't contribute usually to semi-classical saddles. And the analysis is more sophisticated, but it likewise leads to random matrix theory energy level repulsion of black hole microstate. So you end up getting the same kinds of answers that I was advertising before. This is also robust to stringy effects. It's even stable to effects of D3 anti-D3 brain nucleation, which if you're a string theorist, you might worry about other stringy effects trying to destabilize the answer. And at least insofar as our analysis, the analyses we've done, it seems that it does not. So why would I mention this? So in a certain sense, why would it be interesting to take these answers, which seem to be correct in a more general context, namely that of just gravity, Einstein gravity at long distances? Why would we want to see if they make sense in the context of string theory? Like, what's the reason to do that? Well, the reason to do that is that there's actually a historical context in which having wormholes in ADS-CFT is conceptually surprising, and it teaches us something about the nature of the ADS-CFT correspondence itself. So let me explain that. There's a so-called paradox in the ADS-CFT, which I'll call the factorization paradox, which goes roughly like this. Wormholes have posed a problem of the kind that we're discussing, for instance. Wormholes have posed a problem in ADS-CFT since the very beginning of the inception of the subject. So let me explain why they're potentially pose some kind of existential or at least conceptual threat. So here's the basic puzzle. So in ADS-CFT, it turns out that if you compute a partition function of a conformal field theory, some object that you can compute a conformal field theory on some manifold, what this will correspond to is an ADS computation, a gravity computation, where you look at a partition function corresponding to gravity in which you have a single boundary, which is the boundary on which has the same topology of that of the CFT. So let me just give an example. If you're interested in, for example, a partition function in which the CFT is on a torus, then you should consider ADS quantum gravity where it asymptotes, asymptotically far away to a torus. These two quantities should be equal to each other under the ADS-CFT correspondence. Now, suppose that we look at the product of two partition functions. We have a Z1 and Z2, and we just look at the product of the two answers. The problem is that gravity, on the one hand, instructs us that if we have certain boundary conditions, we should fill in all of the, we should sum over all of the spacetimes that can fill in between the two boundaries, that we can fill in between the two boundaries. This includes not only disconnected contributions, but it also includes connected contributions, which from the two boundaries, we can fill in the spacetime in such a way that they connect in the middle. Now, here's the problem. The problem is that what gravity is instructing us to do, namely to include the contribution of wormholes, is at odds with what the CFT tells us should be there. In other words, what the CFT tells us should be there is a quantity which factorizes, is a product of two different quantities which know nothing about one another. Whereas what gravity seems to suggest is that there are correlations which would not allow which would not allow the equation to factorize into two pieces. If there are wormhole contributions in gravity, then this would be at odds with the CFT description, which would give you a product of two quantities. Now, let me make one quick comment, I can answer your question, is that, okay, so in a certain sense, what people have said, or something that people have said, is if in fact we are supposed to include wormhole contributions in the bulk, then it is as if these two CFTs are not actually fully independent of one another. Or rather that when we have two copies of the CFT and we compute these quantities, that they're not independent, but rather that there's some kind of joint disorder average. There's a way in which the CFTs must talk to one another, which would be at odds with the usual formulation of ADS CFT. Namely, if you have ADS CFT where you have multiple asymptotic boundaries, the usual way that we think about the dictionary is that the different CFTs don't even know really about one another. They don't really talk to one another. But if we had to include the wormholes in the bulk, this would mean that there was some manner in which the CFTs have to be mutually correlated in order to get away with these kinds of correlations in the bulk, in order to match both sides. So what essentially, what people have stipulated since the beginning of the correspondence, the way to get around this is to simply hope that these wormhole quantities don't exist. If in fact, in gravity, there are no wormholes, they're not stable, they have various pathologies, then we should not include them, then there is no paradox. If the only kind of viable solutions on the gravity side are these things that are products, then there's no issue. So the question has been, are there wormholes that are stable in certain technical senses in the context of ADS CFT? And if there are, then what does that have to tell us that would alter our understanding of the ADS CFT correspondence? So an early no-go result towards the direction of ruling out these wormholes was due to Witten and Yao, in which they proved that at least in the vacuum, in the absence of matter fields, there are no vacuum ADS wormhole solutions to Einstein's equations for boundaries with non-negative curvature. So they basically showed you can't find solutions of Einstein's equations that look like wormholes under certain technical conditions. So they were attempting to rule out this possibility. However, there were a few examples that were discovered that get around this no-go theorem, where you have matter fields in various ways, in full-fledged ADS CFT. But actually, to this day, they're not actually going to be stable configurations. So they still might be pathological for other reasons. In particular, the most famous examples of these the most famous example goes to a certain instant-time background due to Microstate and Laus in 2004. And there's been some more recent work by Morales and Santos, which they posited maybe one or two more examples, which are also not known to be fully stable to stringy effects.
So I'm just trying to understand how these both can be true. Does the first statement by Witten and Yao mean that there's no stable wormhole solutions to Einstein's equations?
Oh, the difference is here, these are not vacuum. The ones down here are not vacuum solutions. Yeah, so the Witten and Yao says there can't be any solutions at all, regardless of whether they're stable. And here, there are solutions in non-vacuum, which are kind of complicated configurations of instantons or matter fields, but they're not known to be either perturbatively stable in the sense of a saddle point, or if they are known to be perturbatively stable, such as the Morales and Santos paper, they might be unstable to stringy effects like a bunch of grains that could destroy the space-time. So essentially, what people did especially in light of this 2004 result, is that it might have posed, in a certain sense, an existential threat to the nature of ADS CFT dualities. But people essentially ignored it for 20 years and thought that, okay, well, there's some reason that these things are going to go away. Let's not worry about it. And in fact, people did not worry about it for most of the last 15, 20 years.
Isn't the obvious solution that ADS CFT is a damn good approximation, and it will break down if you go into too much detail?
But that would be heresy.
Heresy, okay, sorry.
Yes.
Okay.
I don't know much about it, but my understanding is that some of this is ADS CFT correspondence, at least the originally formula is predicated on like some uniqueness theorems for like the wave equation in ADS. Is it possible that the unique theorems just sort of fail for these topologies?
Well, let's put it this way: there are definitely assumptions which underlie the ADS CFT correspondence. Absolutely, many of the assumptions have been very rigorously tested over the last almost 30 years since post-97. But it's not clear which, if any, of the assumptions goes wrong. And if it does go wrong, that would be interesting. Well, let's come back to this in a moment. I'll give you the punchline, I believe, is that ADS-CFT is not wrong, but we need to change. There's a different way of thinking about this paradox that I haven't told you yet, but I think may in fact resolve it. But I haven't said that. So, okay. So the reason why this was brought to people's attention more recently is that there's new examples of wormholes which were inspired by low-dimensional gravity. For example, in 2 dimensions and 3 dimensions. Now, gravity has a very different character in 2 dimensions and 3 dimensions than it does in higher dimensions. Particularly, there's no propagating gravitational waves in 2 and 3 dimensions. Gravity is topological. It has other interesting peculiarities which give it nice mathematical properties, but render it as being different than gravity in the higher dimensions. So people at least looked at these lower dimensional examples and said, okay, well, there's wormholes there. Maybe we should really start to think about what this means in full-fledged ADS-CFT. So there were some original kind of attempts to take the low-dimensional examples and upgrade them to higher dimensional examples. This was originally done in the work of Sodchenker and Stanford in their 2018 paper. And then the work that I'm telling you about, kind of which generalizes in various ways what they've done, is with myself and Jensen over the ensuing years. But here's the thing: it turns out not only are there these wormholes in higher dimensions, but moreover, we don't want them to go away. We have no reason to throw them out because they encode important and interesting physics. So on the one hand, the way that maybe you should think about it is as follows: if I came along to you and I gave you a Baroque wormhole that was constructed by all these kind of complicated matter fields, and I said to you, we don't know whether it's stable or not, but maybe, maybe this wormhole kind of violates our understanding of ADS-CFT. It would be easy for you to say, well, maybe your construction is wrong. Maybe it'll just go away and we do a more careful analysis, because we really cooked up this really kind of complicated Baroque example. The difference with these examples, these wormholes, is that on the one hand, they're not Baroque. They have very simple configurations from a gravity point of view, and they encode real physics. Whereas if I just cook up something, I just came up with it for the point of, just to prove a point about wormholes. But these actually encode information about the level statistics. So you don't want them to go away. We want that physics to be there. It matches random matrix theory. So this sort of adds to the mystery of what is the role of the wormholes, since they now seem to be there. So the factorization paradox, previously largely ignored over the last 15, 20 years, now has a new urgency because we have these wormholes that we do not want them to go away.
Are they interesting on the CFT side?
Yes, because what they're telling you about is level repulsion in n equals 4 superpositing mills, for example. So they're telling you about level statistics of strongly interacting quantum field theory. And I'll return to this in a moment, because once we see in a slide or two what the resolution of the paradox is, we'll be able to see how we can leverage gravity to learn really interesting things about superpositing mills, and vice versa, once we have a better way of framing what the paradox is and how to potentially resolve it. That's a great question. Okay, so our understanding of ADS-CFT is at stake, being a little over dramatic, but in this world, you might say something like that, at least in the ADS-CFT world. Okay, so how do we get around this issue? So the way around this is even though I've shown you that there's these wormholes that are important in the context of ADS-CFT that make sense from the gravity point of view, it turns out that the right question to ask is, what conformal field theory quantity do these wormholes correspond to? In other words, what is the dictionary between this quantity that you can compute in gravity and this quantity you can compute on the boundary theory? And in a certain sense, the whole factorization paradox lies in the fact that there isn't an obvious answer to the question. So let's consider a particular example in ADS-CFT. Let's consider two-sided ADS d+1 wormhole. So that's what, with two sides, is what we've been considering so far, with a boundary topology which is S1 cross SD-1. This S1 you can think of as a compactified time direction because we're Euclidean signature. Again, it's not particularly so important to know. Okay, so here's a cartoon of what it looks like. And what we're going to do is we're going to fix the renormalized asymptotic lengths of the S1s to be beta1 and beta2. This is like we're going to work as if we're trying to explore the correlations between two black holes with fixed inverse temperatures. So here's beta 1 and beta 2. Okay, so if usually when we fix boundary conditions, we expect in ordinary path intervals that there should be, typically we expect that there's a discrete family of solutions to the path interval if there are any at all. Once you fix the boundary conditions, when you have the PDE like this for Einstein's equations, you expect that either you'll be able to find a solution or a discrete family of solutions or no solutions will exist. We're going to do something that seems initially peculiar, but will pay large dividends, which is we're going to impose an additional boundary condition. Now, it seems as if in ordinary circumstances, if you impose yet another boundary condition, that unless this boundary condition was secretly equivalent to the ones that you already imposed, then you would destroy the possibility just by parameter counting, naively, of the possibility of finding any solutions to the Einstein field equations. Imposing additional boundary conditions beyond the ones that should give you a unique solution would apparently destroy the possibility of having any solutions. So what I mean by the boundary energy, by the way, for those who think about ADS-CFT, is that I just mean that you look at the integrated holographic stress tensor on each of the boundaries and then divide by the temperature, or by the inverse temperature multiplied by the temperatures. So that's what I mean by fix the energies. Amazingly, however, once we impose these two boundary conditions plus this non-standard boundary condition, we actually find a new saddle point of the Einstein equations. And this new saddle point, it's a genuine saddle point, corresponds to a wormhole with a bottleneck size that has a volume that goes like the total energy that we fixed. So there's a new saddle point. And I sort of premise this on it being counterintuitive that such a saddle point will exist. I can explain to you why it doesn't violate actually any assumptions about the Einstein equations. But there's a new genuine saddle, a macroscopic wormhole saddle. And what it corresponds to, it turns out, is this. So if you carefully track through what these boundary conditions mean, what it's doing is that it's taking two copies of the density of states of the CFT, or of the theory that you're interested in. It's taking their Laplace transform with respect to beta 1 and beta 2. And now there's also a delta function constraint that constrains the energies to have to add up to some total energy. So the point is that the bulk wormholes, mainly the wormholes, these are in fact these are related in a way I can explain to the wormholes I was telling you about this entire time. This is the cleanest manifestation of them. They're dual to a quantity in the CFT, which does not factorize. That's the point. The thing which it corresponds to in the CFT has a constraint which ties together both of the CFTs. So in other words, these wormholes are dual to something on the CFT side, and not in which the two CFTs factorize, but in which they are tied together by an energy constraint, which in fact can be regarded as a non-standard but gauging varying boundary condition, which ties together the two CFTs. So this provides an appealing resolution to the factorization paradox, at least for these kinds of contributions, the particular kinds of wormholes that I've told you about, because it obviates the need for factorization. The quantity shouldn't factorize anyway. But it also opens up a new possibility, because it opens the door to new non-perturbative effects in ADS-CFT, which involve boundary conditions which couple the two CFTs. Now that we know that this is the right boundary condition which describes the wormholes, we can now go to town and understand other wormholes, which also tell us information about level statistics of black holes, or on the flip side of it, about the conformal field theory, which describes the black holes. So let me give you an example of this. This is related to what Peter was asking before. Let's consider one of these two-sided wormholes, and usually let's consider the context of n equals 4 super Yang-Mills. So we have two CFTs, one that describes each of the asymptotic boundaries, which are each at a fixed coupling of the Yang-Mills coupling. Now, suppose we wanted to do something kind of unusual. We wanted to look at level statistics between n equals 4 super Yang-Mills at one coupling and one that's at a perturbed coupling. This would be an unusual thing to do, but it's something that turns out, if we follow our machinery that I've described to you, this is the answer that we can get from a bulk gravity computation. It's a slightly complicated looking answer, but it turns out that so what you see is that there's an exponential decay. There's this complicated exponential, which has, it's like e to the minus some constant times t. times the linear ramp. And what this tells us is that as we try to look at the level correlations between one theory and another one with a perturbed coupling, that as we detune the couplings from one another, the level statistics exponentially decorrelate. They look less and less like one another. But what's interesting is that this prediction, in fact, precisely agrees with the prediction of random matrix theory. There was a slightly less well-known random matrix theory computation done in the early 90s, which actually gives you a precise prediction for what you should expect if you looked at level statistics between, say, Yang-Mills, N equals for super Yang-Mills and a copy of itself with slightly detuned coupling. And this, in fact, precisely that you get is the answer that you would expect to find. Like the constant is this is a quantitative answer. It agrees precisely with the predictions of random matrix theory. So again, this is a gravity computation in ordinary ADS-CFT, which is agreeing with a very non-trivial random matrix computation, which tells us information both on the gravity side and about the nature of the CFTs. So now let me make some conceptual points, and then I'll conclude about what I think this all means more broadly. So we found that a large class of wormholes in ADS-CFT should be are due, to a joint smearing over the energy levels of two CFTs. In other words, that we had to do this smearing where we tied together the energies of the two CFTs and force them to add up to a common energy in order to get to access these coarse-grained level statistics in gravity. So it's recently been emphasized that the gravitational path integral, namely that when we try to stick Einstein gravity into Feynman's path integral, that we can only access simple functions of Newton's constant. This is for a very simple reason, which is that when you have a path integral and you have some small coupling, if you compute perturbation theory, then you get answers which are polynomial in the coupling, lambda plus lambda squared plus lambda, whatever. If you look at saddles, those look like quantities in which the lambda is upstairs in the exponential. So it was recently kind of emphasized in a paper by Schlenker and Witten that in gravity, the only things which we can access in the semi-classical path integral are those which have a simple dependence on Newton's constant. Whereas there are ostensibly many effects in gravity which have non-simple dependencies on Newton's constant, and as such cannot be accessed just in the semi-classical gravitational path integral, namely just by doing effective field theory where you stick Einstein's equations into the Feynman path integral and see what you get. So there's effects that we cannot access. So a different way of saying this, which is fleshed out in this paper to appear with Christian, is that this in fact implies that the gravitational path integral, in the context of the calculations that I've been sharing with you, can only access smeared energies and smeared energy eigenstates. To say it in a different way, if you're interested in studying the physics of black holes, there's no way that by doing a gravitational path integral, you can access a particular black hole microstate. What you are able to access is a smeared band of black hole microstates in a certain energy window. And the precision of that is limited in a certain sense by the fact that you're doing a path integral computation. It's limited by the fact that you can only access certain functions of the Newton's constant. So you can only access not individual microstates, but smeared bands. You can't access individual energies, but you can access quantities which are smeared over energies.
Except the ground state, right?
Right. So it turns out that, okay, so this is exactly this next point, which is that the things that we've been interested in this talk are black hole physics, which are above the threshold for having, there's a certain energy above which you have microstates which correspond to black holes. Now, the black hole physics is not integrable, it's chaotic. But if we are below the black hole threshold, then we can bring to bear techniques of integrability and supersymmetry to actually pin down physics in which there's no black holes. For example, ground state information, low-lying energies. That information is integrable, and we can access it via other methods and understand those states precisely. But as soon as we're in the regime where we're interested in kind of chaotic black holes, that's the case in which we cannot understand the microstates individually, at least using semi-classical techniques. So in other words, the only thing that we can do to study the black hole microstates, or at least the only two things that I know how to do, is to smear the energy domain and use a semi-classical description, in which we have sort of smooth spacetimes, which are giving us information about smeared information about black holes. Or what we can do is if I give you the CFT n equals 4 super Yang-Mills, I give you, a quantum computer, and you can diagonalize the Hamiltonian, and you can access the energy eigenstates, then you could look at those and potentially understand something about the black hole to which it is doing. Those seem like the only two options. We've explored the first option in this talk. The second option is more futuristic. We don't know how to do it at present. Now, the story that I have told you, in fact, relates to a very old set of ideas, in fact, a lot of which were developed at Harvard here by Eric Heller, namely that of semi-classical quantum chaos. Let me make some comments about this, and then I'll conclude. So the idea, if you want to access chaotic physics, for example, black holes, so what we're doing is we're smearing over energies to gain a semi-classical description. This idea in the context of chaotic systems, usually few-body quantum mechanics, goes back quite a few years. But if you want to access a semi-classical description of a chaotic quantum system, then you should also smear over energies. In a certain sense, what we're seeing is these ideas being ported into quantum gravity as of late. So here's a picture, for example, of periodic orbits of a billiard stadium. And this technology of smearing over energies to access a semi-classical description of a chaotic system, for example, by looking at closed orbits, was developed by Michael Berry, as well as Bogomolny, Heller, and others, Heller's at Harvard, in the 70s and 80s. And Berry, in particular, emphasizes that without the energy smearing, a semi-classical description of a chaotic quantum system is impossible. There's no way of, in general, describing a single eigenstate of a chaotic system by just using semi-classical methods. I believe that what that should mean in the context of black holes is that there is no sort of fully smooth space-time description, at least at the level of like a solution to the Einstein field equations, which should really describe what is going on with a particular black hole, unless the black hole is special in terms of features of interoperability. It has other qualifications. Yes?
So in the diagram, is it that the up and down line is just smeared out?
Oh,
the vertical.
sorry, I should say what the figure means. Suppose that you're interested in understanding the quantum mechanics of a particle bouncing around in the stadium. It turns out that there are nice classical configurations, which are just the periodic orbits, the ones that are like closed loops. It turns out, for reasons that I don't have time to explain, that these are ones that are important for understanding features of the energy, of the spirit energy spectrum.
So is it that you'll have like multiple chaotic states corresponding to a single class, or is it more complicated than that?
It's that essentially that if you want to understand information about a smeared band of energies, then you look for periodic orbits for certain quantities which have similar energies as the quantity that you wish to study. So let me summarize and then I'll conclude. So what this tells us is what we can and probably cannot learn from ADS-CFT, at least in the near future. For black hole physics, which is chaotic, we can only leverage semi-classical methods to access energy smeared quantities. I think that's a lesson. This is the regime, namely the smooth quantities, for which semi-classical spacetime even makes sense in the first place. That semi-classical spacetime should correspond, at least as far as black hole physics is concerned, to energy smeared quantities. Now, that is to say that we can only learn about the microstructure of black holes in spacetime in a statistical manner in the context of ADS-CFT, i.e. by looking at statistics which are ingrained in the energy average quantities. That's the story that I tried to tell you about today. Now, in principle, it's possible to access black hole microstates directly. For example, by diagonalizing the CFT Hamiltonian on a quantum computer or an enormous classical computer. But even if we could do so, the holographic dictionary, which describes, so given this state on a quantum computer, the thing that tells us how to describe a black hole or its interior might still be exponentially complex to compute. In other words, translating the CFT into the gravity description, even given it, even handed, still might be impossible effectively. And we don't actually know of a good prescription for doing this in any case. So I'd like to conclude by just making a few kind of comments about how this, I think, fits into a broader story. So there's an old famous story that we all know about Einstein when he, in his work on Brownian motion, in which he looked at the statistics of pollen grains suspended in water, seeing how they jiggled on account of the Brownian motion. And then it was in doing so, he was able to infer the existence and size of atoms. This is particularly surprising because the pollen grains and the fluctuations of the pollen grains that you can see under a microscope, even with the naked eye if you really squint, are orders of magnitude larger than the atoms out of which the water molecules are composed. Nonetheless, by looking at these long-range statistical quantities, these things that you can see almost with the naked eye, you can infer properties about the existence and the size of the atoms in the water molecules. What we're doing, I think, or what is going on here, is a version of this in quantum gravity. There's a mesoscopic description of quantum gravity, as I'll call it, something which is sort of statistical or long range. By looking at statistical properties of gravity on intermediate or long distance scales, we can use that to infer properties of the microscopic structure of space and time. That's what's going on in these computations. That is, non-perturbative effects in quantum gravity, valid and effective field theory, contain statistical signals of UV phenomena, namely the microscopics of space and time. In some fashion, it is our obligation to try to decode it. I think this has the potential to open new horizons in quantum gravity. Let me end with one last little anecdote from one of my favorite short stories by Borges. So Borges has a short story. This is almost the entire story. It's called The Inexactitude of Science. He says the cartographers' guilds struck a map of the empire whose size was of the empire, which coincided point for point with it. In the deserts of the West, still today, there are tattered ruins of that map inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. Borges tells a story in which there's a competition to make a progressively more detailed map of the kingdom. And it ends up spiraling out of control to create a map that is the size of the kingdom itself and is thus completely useless. I think that this is an apropos lesson to end on, which is that often we can only make sense of the world by viewing it from a distance. So thank you so much.
Thank you, Jordan. We have time for a few questions.
I have a question. So when you were talking about the density of states, the density of energy states, and the fact that it has this form, and I think someone mentioned symmetry before.
Yeah.
When I think of that, when I see something like that, I think of symmetries. And I wanted to understand a little bit better, are there some symmetries here that go between ADS and CFT? And is there a phase transition that occurs at some point that causes those long range energy distribution?
Yeah, so there's a few different effects to sort of disentangle here. So on the one hand, often when we look at these statistics of the energies, these black hole microstates, we're usually interested in looking at all the quantum numbers which are conserved quantum numbers, all the symmetries, and fixing them. So for example, if there's charge, we'll work at a sector of fixed charge. If there's angular momentum, we'll work at a sector of fixed angular momentum. So as such, we've sort of already accommodated for the symmetries of the black hole in order to disentangle which degeneracies of this, in other words, you expect that there might be degeneracies in the spectrum by virtue of the symmetry. You don't expect them generically. So once we've accounted for the symmetry, what is left should look generic in a certain sense and should not have this degeneracy. Now separately, there's a question of an ADS-CFT is why you expect, for example, that the anti-de Sitter space quantum gravity looks like a conformal field theory. One of the early indications as to why this was the case is that a conformal field theory, its conformal symmetry, can be mapped onto the symmetries of anti-de Sitter space-time. That was one of the early reasons in, say, the early 90s that it was anticipated that there would be such correspondence. Now, exactly how those symmetries, exactly how those interplay with the black hole story is a little bit more complicated. Maybe we could talk a bit about more offline, but I want to just emphasize they're slightly different notions, but how do I say is that what we're really interested in is the quantum numbers associated to the black holes, which in some cases are inherited by properties of the space-time in which it lives.
Yes, Mike.
Yeah, so I understand kind of intuitively why energy states of heavy nuclei might be described by random matrix statistics. That's really surprising to me, though, for black holes. I was just wondering, what's the intuition about why black holes are chaotic, and what's the specific definition that's meant to that?
Yeah, so I would say that there's sort of two pieces of intuition. One of them is that any system which, okay, so let me give you some intuition for why it's chaotic. There's many different computations which suggest this, but let me give one that might be the most, intuitively familiar in the context of the black hole information. If you have a system for which, if you put information into it, And the information that comes out in terms of the Hawking radiation was purely thermal, or thermal up to really exponentially small corrections. Then it must have done a really good job of scrambling around the information that you threw into it. You put in a book and you get a thermal gas, it must be really chaotic, at least intuitively, in order to move, basically make it so that all of the relics of what you threw in are very, very hard to kind of pick out of the outgoing distribution, even a long times. There are other more precise versions of this that can be set even with shorter time scales than just the evaporation of the black hole, but that's some intuition as to why you might expect it to have the outcome. But the other answer to your question is, the thing that you in general expect is that any quantum system which is not integrable, which is most the standard model, for example, is a chaotic system. All, in a certain sense, integrable systems are a lamppost effect. There are systems that we can solve exactly by hand, but most systems in the world are not of that kind. And as such, most systems are chaotic, and the ones that are chaotic generically have their energy levels described by random matrix theory, including black holes. So in a certain sense, I was just indicating to you that there's something special with black holes. They're really chaotic, whatever it is. But in fact, there's a more mild thing to say, which is that any system which is quantum, chaotic, generic in a certain kind of way, now whether it's standard model or just some condensed matter system, they're also going to have chaotic level spaces, or those that recapitulate the results of random matrix theory. It's very universal in that sense.
Okay, a final question from Ramesh.
Okay, maybe Dominic.
Sure. We can do both if they are.
I had two questions.
I also had two, but if you have a short one, go ahead.
I guess the first one, sure. So I was curious about the boundary conditions.
Yeah.
It seems like you can just get different topologies of the boundary conditions. And how do you know what boundary conditions you put? Like, it seems like you'd have to decide that you want wormholes in your.
Yeah, so what you do specifically is that you work at a fixed topology of your choice, and then you impose the boundary conditions on the asymptotic regions. So the way it works at a technical level is that you pre-decide what topology.
So you have to decide that you want wormholes in your.
Yeah. It turns out that it works for a variety of wormhole topologies. I mentioned some specific ones, but there's a whole large class which works.
So thanks for this great talk. Okay, almost feel like I understood it. Okay, so you showed, it's not just that random matrix theory gives similar results. In fact, you said it gives exactly the same results with every constant in the right place, the root pi's and the 2's and all that. So is that because these two very different problems are doing exactly the same calculation, or is it more of this magic that there's two different calculations, but they give the same answer? How should I understand it?
That's a great question. In fact, it's a great question to end on, because I think it's so here's what I think the story is. There is magic going on, but here's why I think there's magic going on. Because the calculations are very different calculations.
Okay.
It's very different. What's interesting, however, is in the random matrix theory calculation, the coarse graining, is sort of explicit. The manner in which you derive this, if you have a random system, there's sort of some coarse graining going on in a particular sense that gives you this answer for the coarse grain level system. What's interesting is that gravity at long distances, in the context that we can compute in the path interval, is also apparently doing a similar kind of coarse graining, even though the calculation itself doesn't, at surface, at face value, seem to indicate that somehow what gravity is providing us with, what quantum gravity and the path interval is providing us with, is this sort of coarse-grained, what I'm referring to as mesoscopic description of the underlying microscopic degrees of freedom of space and time. And the fact that it is providing us this information in a way which can be so quantitatively and precisely matched is, I think, some kind of deep indication of some feature of quantum gravity that we don't understand. The fact, for example, that I was saying, in the pollen grains, the fact that you can look at the fluctuations of a pollen grain and infer something about atoms is kind of magical. It's surprising. And I think that there is a similarly surprising phenomenon which is happening in gravity.
Amazing.
All right, let's make a final applause for Jordan.